So we're on section 7.2. Now, for the benefit of people that aren't watching these videos in sequence, but are just dropping in here, there is nothing new on chapter 7. I'm just going through the examples one at a time. We know all the maths that we need to know. We just need to look at some examples. So all I'm doing here is examples. Now, we have some modelling assumptions that we're not very used to here. A smooth bead Y is threaded on a light and extensible string. So if we've got a smooth bead, then that means there is no friction, okay? Because the bead is smooth, so it's sliding up and down this thing with no friction forces involved. And it's threaded. Now that means it can slide up and down. Now, in terms of our modelling assumptions, what that means is the tension in the string is the same all the way through. We've got a tension there and a tension there, and these tensions are the same. If we had the same thing and it told us that it is tied on, well, think about it this way. If that was threaded and you moved the bead this way, then what would happen is once the bead's here, you'd have this sort of situation, wouldn't you? The string, you know, as the bead slides. Just picture what would happen in real life if you moved the bead. Your string would sort of move into a V shape and so on. Now, if the bead was tied on here, what would happen if I tried to move the bead to the right? Well, this thing here would move the bead upwards, and then this string here would kind of go slack, wouldn't it? Okay, can you just picture what would happen if you actually had this glued or tied to this bead here instead of this being a bead with a hole through it threaded on the string. Now, what's the difference there? Well, the difference is, look, this string here is tight, so there is a tension in it. This string here is slack, so there's no tension there. So if you have a bead threaded, the tension is constant. If you have a bead tied, then you can have two different tensions. Tension here and tension here might be different. So we'd label them T1 and T2. Perhaps we've not seen that very much, but it's just using a combination of things that we know with a bit of life experience. So a smooth bead is threaded on a light and extensible string. The two ends of the string are attached at points X and Z on the same horizontal level. The bead is held in equilibrium, so we're told equilibrium. We're immediately thinking turning effects, moments, balance out clockwise and anti-clockwise, and forces are equal. Forces balance out, the net force is zero. There's no turning effects going on in this question, so we're just going to look at balancing out the forces. The bead is held in equilibrium by a force of magnitude 8 newtons, acting parallel to Zx, so this is a horizontal force as well. The bead Y is vertically below X, and this angle is 30 degrees here. So, if that angle there is 30 degrees, then this angle here is 30 degrees by Z angles, look, or alternate angles if we want to use the proper word for it. Find the tension in the string and the weight of the bead. Now, we've got these three forces. Then, if I just left the diagram like that, then there's nothing pulling downwards, so this thing must be accelerating upwards, so I must have a force going downwards, and the thing that I've missed off at the moment is the weight force pulling downwards. Now if I just cover this up, can you see that that diagram now looks exactly like one of the diagrams from section 7.1, so we can now deal with this no problem. We just need to do forces left, forces right, forces up, forces down. So let's look vertically first of all. The force is balanced, so we're going to resolve vertically, and we're going to get T from this tension. T sine 30 from this tension, and they're both pulling up. Downwards we've got the weight, and this one is horizontal, so there's no vertical component. There's my equation number 1. Horizontally there's no acceleration, so the force is balanced out. We're going to resolve horizontally. 8 newtons pulls to the left. This one doesn't pull left or right. This one doesn't pull left or right. This one is pulling to the right, and how much of it is pulling to the right? Well, T cos 30. As discussed in the last video, I have two simultaneous equations and two unknowns. The mechanics is done. All we have now is algebra. So we've got to fiddle around with the algebra. And this one actually is fairly quick to see. I'd rearrange equation 2 like that, and then I'd take that and substitute it into equation 1. That's probably the way I'd go. And that will find us the weight of the bead. Once we know the weight, we can work out the tension. Example 4. We've got a mass of 3 kilograms resting on the surface of a smooth plane which is inclined at an angle 45 degrees to the horizontal. So as you do these, start drawing things down. We've got a mass of 3 kilograms, so that has got a weight force of 3 times gravity pulling downwards. There must be a reaction force because otherwise this thing would be accelerating downwards through the plane. Those two forces we always put on whenever we have an object sitting on a plane. It's a smooth plane, so we've just been told we can ignore friction. The mass is attached to a cable which passes up the plane and along the line of greatest slope, then passes over a smooth pulley. This is the first one of our pulley questions, and we'll see lots of these. It's the first one since the AS level course. The cable carries a mass of 1 kilogram, so that's a 1g force pulling downwards, and from AS we should be used to putting on that this is a tension here and a tension here. It doesn't actually say that we can model the cable as a light and extensible, but yes it does. If we read another sentence, it says the masses are modelled as particles and the cable as a light and extensible string, therefore the tension is the same all the way through the cable. There's a force of P newtons acting horizontally on the 3 kilogram mass. So I like to put my forces on starting at the object and moving away from that, and that's acting horizontally. And the system is in equilibrium. So I'm just going to put on here, look, there's a 45-degree angle there, should I need it. So what do we get? Well, first of all, I'm going to put a dotted line in there and remind myself that that is a 45-degree angle. From AS level, we remember that when we have a pulleys question, we cover this bit up and we look at this part of the system, then we cover this bit up and we look at this part of the system. So I'm going to label this bit, they're not labelled already, so I'm going to label this A and I'm going to label this B. And I'm going to say at A, I'm going to start by looking parallel to the plane. The system is in equilibrium, so all the forces balance out. Oh, this one hasn't got a label, we'll call that R. So parallel to the plane, what do we get? Tension is pulling it up, dealt with that force. This one here is pulling it up parallel to the plane, and what component of it? Well, it's P cos 45, because it's adjacent to the 45 angle. So P cos 45, that's not pulling it up or down, that's pulling it up, that's pulling it up. We're ignoring these forces because we're only looking over here, so working through the forces, this is the only one that's left, and that is pulling down the plane, but not the whole 3G pulling down the plane, just 3G sine 45 degrees, just the component opposite the angle. This component here is pulling down the plane. There's my first equation. Going perpendicular to the plane. Again, I'm resolving forces because it's not accelerating, so I get, pushing outwards from the plane, I get R. That tension is parallel to the plane, it doesn't push out, doesn't push in. This one here, opposite the 45 is the component that's pushing into the plane, so R equals P sine 45 degrees. And then this one here, the component adjacent to the 45. There's equation 1, there's equation 2. I've not finished yet though, because we haven't considered the forces over here. So at B, going vertically this time, tension equals 1G. There's equation 3. I've got 3 equations written down. So now I should be able to read the last bit of the question and see what they're actually asking me to find. And it says calculate the magnitude of P. So P is something I want to know. Let's get a different pen for this. So we want to know P. The normal reaction between the mass and the plane, I labelled that R, so I need to know R. And state how you've used the assumption that the pulley is smooth. Right, fine. So I need to know P and I need to know R. Well, if we look at that, this equation's got a P and an R in it, so that won't do. I'm not going to be able to find it from there. But this equation's got a P and a T in it. Well, that won't do because I can't find P from there. But on the other hand, here's my T. So if I take this T and substitute it into equation 1, that'll help me find P. Once I've found P, I can put that into equation 2 and find R. In other words, 3 equations, treat them all as simultaneous equations, and the answer pops out. How have we used the assumption that the pulley is smooth? Well, smooth means no friction. So if there was friction in this pulley, well, again, imagine this. If there was lots and lots of friction in this pulley, then you can imagine, what's the best way of saying this? Imagine it was so much friction that it was basically sort of stopping the rope. Can you see that I could, if this was really full of friction, can you see that I could pull on this as hard as I want? Maybe I could even sort of hang off it as my little stick man, hanging off this rope. And if there's enough friction, he's not going to fall down, is he? Okay, you can put your whole weight on it. So that would mean that this could be pulling really hard, and then somebody can maybe come and push this box up, and there would be a slack in this rope. So the tension here is not going to be the same in the tension here if there's friction. If there was an enormous amount of friction, you might even have this sort of situation, which just, I'm explaining the extreme case to hopefully get the point across to you. So the tension being the same all the way through the rope is an assumption that we can make because the rope is light and inextensible. Well, because the rope is inextensible, the light bit doesn't really matter. Oh, I suppose the light bit does matter, because if the rope had a mass, then this part of the rope will be supporting the mass of this part of the rope. So light and inextensible helps the tension be the same, but also we need the pulley to be smooth if we're going to get the tension the same all the way through the rope. Okay, those are the examples for section 7.2. Now, there are other sorts of questions in the exercise here, but they all follow the same methods, right? You look at it, they're all in equilibrium. For the moment, there aren't any that involve moments, I don't think. These are all forces up and forces down, or possibly forces parallel and perpendicular to a certain direction. So write the equations down that you've got. You might need to consider the one half of it and the other half of it separately, but once you've written the equations down, the mechanics is over. If you can get to the equations, you're there. What equations are you going for? It's balancing forces out, okay? It's all static for this exercise, so it must be balancing forces left and right, up and down, parallel and perpendicular. So look for those kinds of equations, and once you've got those, your answer should come out in the end. Good luck with that section.